I think the easy
at position I, if HI is equal to 0, and we say something that goes on over here and over here.
它有3个，它是怎样？对啊，不知道为什么。哦，你说话了解，我现在也不信任其他电视。测试，有。Would you want to test again?
Yeah, let's just try it. All right. Okay? Okay now? Okay.
This might be the universe.
The comment was made, this is the universe rebelling against homological algebras, but we will bend the universe to our will now. All right, so where were we? So an oriented I simplex, this is an... The universe doesn't like to be mocked. That's the lesson here. Don't mock the universe. Maybe it's a sign that David's point about mirror symmetry, maybe we're onto something with mirror symmetry here. Maybe that's the sign. Can you guys hear okay right now or not? I'm not sure if am I recording? It's okay? All right, okay, so I'm not going to make any more comments about the universe. So an oriented I simplex is just an ordered I plus 1 tuple. So for example, a 0 simplex is just a vertex. A 1 simplex we think of as an edge, oriented. A 2 simplex we think of as a triangle. And the triangle will have an orientation. So this would be, usually we'd write it something like this. So for the orientation. So that's what simplices are. And then a simplicial complex. So delta is simplicial complex. Is a union of simplices, simplices, glued the same way, so in the interest of brevity, the same way as we glue the faces of a fan. In other words, if I have a face of a simplex, that's part of my simplicial complex, 2 simplices, which meet along a face of both of them and so on. So that's pretty straightforward. And then I want to define simplicial homology, so then I'm going to make C sub I of delta. So I was handed a simplicial complex, which might, for example, look like something like this. Here's a simplicial complex. Maybe this triangle is open and this triangle is hollow, right? So there's an example of a simplicial complex. And I'm interested in the topology of an object like that, right? So C sub I is going to be a free, let's maybe, if we want to decorate it, you can add whatever coefficients you want, where R is some ring. I'm typically not going to write the ring down. You can use whatever coefficients you want. So this is going to be a free R module with basis the oriented I simplices modulo a relation that if I have 2 simplices, say, and I've changed the ordering of the vertices, change the indexing of the vertices by a permutation sigma, then maybe I call it gamma, that is equal to V sub I 0 up through V sub I k. There's a k simplex, is the same thing as minus 1 to the sine of the permutation sigma, which is V sub J0 up through V sub jk and sigma is a permutation that takes this to this. So all I care about is the sign of the permutation when I change the ordering of the vertices. All right, so what? So now what I do, and I have to have a differential, and I'm going to write d sub I of some gamma. This is an I simplex. Say that I is equal to v sub j0 through v sub ji is just an alternating sum k equals 0 to I minus 1 to the I vj0 vji hat, leave that one out, up through vji. That's not I, that's bjk. Right, so all that we do is we take some k-dimensional face and we take an alternating sum of its k minus 1 dimensional faces. So let's see this in action on a simple example. This is, for those of you who've seen simplicial homology, don't worry, I'm going to go through this very fast and we'll get to something interesting. So suppose that our delta is equal to a hollow triangle, 1, 2, 3, with this orientation, right? So I've given an orientation. So my simplicial complex has edges 1, 2, 2, 3, and 3, 1. Those are my edges. And vertices 1, 2, and 3. And we write down. So I have a basis. The 1 chain, C1 of delta, has basis 1, 2, 2, 3, and 3, 1. C0 of delta has basis 1, 2, 3, and we write down this matrix 1, 2, 1, 3, 1, 2. Let's use this orientation 2, 3, and 3, 1, 1, 2, and 3. The boundary of this, when we parse this definition of the boundary operator, is I'm going to take, first off, it's going to be leave out the first vertex, so I'm going to leave out vertex 1. So I'm just going to have vertex 2 with a positive sign. So the boundary of, and this, I screwed that up, so this should be 1, 2 across the top, 2, 3, 3, 1, 1, 2, and 3. So the boundary of 1, 2, you can see it's going to be 2 with a positive sign and 1 with a minus sign. So it's going to be minus 1, 1, 0. Boundary of 2, 3 is going to be, and you can think of this as head minus tail for edges, right? So this is the head is 2, the tail is 1. Similarly, 3, 2 is that. And 3, 1, the head is 1, the tail is 3. So there it is, and there's nothing else. So we compute, and when we compute the homology of this, you can see that the kernel of this is generated by 1, 1, 1. So if we're using z coefficients, h1 of this thing would be a free module with 1, 1, 1 as the basis. This matrix has rank 2, so H0 is the co-kernel of this. So H0 would be what? Help me out. It would just be what? H0 is the kernel of this map, not 0. H0 is the kernel of this, which is everything, right? Modulo the image of this. So the kernel of this map is going to be, the kernel of this map is everything. This is a Z3, right? If we're using Z coefficients, so this is isomorphic to Z3. And then I'm modding out by something. This is going to be a Z2. I'm being cavalier here, so this is isomorphic to Z. And so we get that both H1 and H0, H1 and H0 are both Z, isomorphic to Z1. And what this represents, of course, is that when you first have a course in algebraic topology, if you've had such a course, is that simplicial homology is supposed to count the number of holes of various dimensions. So with the caveat that I need to say something special at position 0. So H1 counts the number of one-dimensional holes. That's an S1. This is a topologically an S1, so I have a one-dimensional hole. H0 is a little funky. What's a zero-dimensional hole? So what we sometimes do is to create something called reduced homology. So if I add in the empty face, which people like to do, then we actually decorate this with a little twiddle. Notice adding in the empty face only is going to impact our H0, right? I've only added a thing there. Why would we do this? And it's an easy, fun exercise to check that H0, or the rank of H0, or the dimension, let's say rank H0 twiddle is equal to the number of connected components. So in particular, for this example, the H0, if I added in a Z here, then I'm going to have and this map would be, this is mapping everything to 1, so this is 1, 1, 1. You send everything to the generator here, and then the kernel is going to be, of this map is now two-dimensional. The image is this, it's exact here, and you get H0 would be 0, and it's because there's one connected component, right? So this is...
You said the rank of H0 tilde is the number of components, maybe minus 1?
Minus 1, sorry. So there's one connected, yeah, that's exactly right. So the point is that if you're, why would you want to do this? The point is that somehow if your object is connected, then there's not interesting zeroth homology. And so you want the H0 to vanish. So, but otherwise, if you don't do the reduce, then it's just counting the number of connected twins. Okay, so that was a toy example. We're way behind where I wanted to be, but it is what it is. So that's simplicial homology. Simplicial cohomology, maybe I put it over here. For cohomology, I simply take I'm taking hom of my C sub I into R. So I take, when I do this, of course, when I take hom of C into R, this is dualizing things, so now I decorate this with an upper arrow and I get that. So it's the same sort of basic construction. Any questions so far? This should be hopefully reviewed for most of you. If not, we're going to get to some interesting things shortly. So now singular cohomology, example 2. So now the objects that I have are maps from the standard unit simplex I guess the I cochains, I should say the I cochains, maybe. The I cochains are maps from the standard unit I simplex into your space X. So I have an arbitrary space X, and I take maps of my units I simplex into X. And so then it's easy to check that if I have two spaces X and Y, and I have some map between them, that I can pull back chains on here to here, so I get a map from Ci of X by pulling back to Ci of Y. So this is one property of singular homology. Next property that we're going to need, so we're going to be using singular cohomology, is that if I have a map, say Y to X, which is an inclusion, which is a deformation retract. So I have a map backwards called R. I'm just going to keep going, and eventually there'll be no chalk left. Such that if I do I and I do R, I get the unit, so Ri is equal to the unit on Y, so the identity on Y, and the other direction, so IR is homotopic to 1 sub X. This is called the deformation retract. Then HI of X is isomorphic to HI of Y. In particular, a contractible space. So what does contractible mean? It means there's a deformation retract to a point, right? So something like, a disk can be smoothly contracted down to a point, and then we get that has contractible space C for contractible has all the HI of C equal to 0 if I is not equal to 0, and if I is equal to 0, it's just equal to whatever the coefficient ring is that I'm using. So that's deformation retracts. What other properties do I want to mention about singular homology, singular cohomology? The other one perhaps is an example that we need. I just mentioned this. So HI of Sn minus 1 is equal to, let's say, of R is R if I is equal to 0 or n minus 1, 0 else. And let's see, for nice spaces, HI X, singular cohomology of X with R coefficients is going to be equal to HI check cohomology of X with R coefficients. And I'll say what this, we have to, this is like in Pascal where you have a forward definition. This is to be defined. So this is coming in part 4 today as the check cohomology. Two last things. Cohomology. Why do we like cohomology better than homology? You might say, well, it looks, all I'm doing here is I'm homming from my I chains into R, so then I get these I cochains. And the point, and the reason cohomology is nicer, it doesn't seem like this would be the case, but in fact cohomology has a ring structure. So cohomology has a ring structure. And so if I have some Ci in, times Cj, where these are classes in Hi and Hj, then I have to tell you, remember these are operators, this is supposed to eat, so these are maps from a standard unit simplex, this is going to be equal to, this is going to be in Hi plus j, this is supposed to eat an I plus j simplex, so I have to tell you how it does that, so Ci, Cj, eating a V0 up through V sub I plus j is by definition Ci on the first, on what's called the front face, V0 through Vi, times Cj on the back face. This seems like a weird definition, but it works, and you can check that this actually, that Ci Cj is minus 1 I plus j Cj Ci. So cohomology has a ring structure, and the last thing I want to say about cohomology very quickly is what did we get for a product space? So if I have a product space x cross y, then we have the Kunath formula, which says that Hi, or Hi of x cross y, is almost as nice as possible. It is direct sum Hi j plus k equals I of Hj of x tensored Hk of y. This is an additive decomposition. And so, quick example of Kunath formula. What's the nicest sort of product space that we've been working with so far? Torus, right? So we should do this for the torus. So what's the example? Tn is C star set to the n, which we know is homotopic to S1 to the n cross R to the n. So by Kunath, the additive, the Hi, or the whole cohomology ring of Tn additively, let's say let's just say Z coefficients, who cares, is going to have a decomposition that looks like a direct, so it's going to be sort of a bunch of these, the cohomology rings of just plain old S1s, a tensor product of such things. But this is an additive decomposition, and the problem is that in fact, what the cohomology ring of the torus really is, if you work through it, it's an algebraic topology first course, is that the cohomology ring of Tn turns out to be, it's still pretty darn nice. We take the exterior algebra on M, right? So this is just Z to the n. And remember, exterior algebra is like symmetric algebra, except when I multiply xi times xj, I get minus xj xi, right? So it skew commutes. And that little sort of twist means that things are very different for the exterior algebra, right? The exterior algebra on if I had an exterior algebra on two things, on a two-dimensional vector space with basis E1, E2, then the exterior algebra looks like in its graded pieces, the unit E1 and E2, then I have E1 wedge E2, right? And that's it, it dies, because anytime I have anything else, as soon as I have, because of the skew commutativity, everything squared is equal to 0. So I have this little weird ring here. So that's the cohomology ring of torus. And if I had some choice of coefficients R, then this is just tensored over Z with R. So there's the cohomology ring of the torus. So that was the end of section 1, which is supposed to take 15 minutes. I'm going to give myself a 5-minute injury delay. Since we've got a soccer game coming up, I had an injury time of 5 minutes for when my thing was dead. I said that was my injury time. So that was the quick singular simplicial. So those are the examples to keep in mind. So now it's homological algebra. Section 2 is homological algebra boot camp. So the only tool that you need in homological algebra is something called the snake lemma. And the reason I wanted to mention this today is when David was proving that we have this exact sequence, all that was happening here was the snake lemma. And so proving this is an exact sequence is easy. So the snake lemma says the following. Suppose that I have the following. A1 goes to A2, goes to A3, goes to 0. Sometimes you'll see this with left exactness here, but we don't really need it, so I'm going to not put it in. B2, B3. So I have a right exact sequence and a left exact sequence, and I have maps between them. Then, so this is exact and this is exact. Then, if I look at, let's call this a D1, D2, and D3. Then I have some maps. I have kernel of D1, which I'm going to write, I'll just write cur D1, cur D2, cur D3, and maybe I'll write C for co-kernels, C1, C2, and C3. Those are the co-kernels. So I have, of course, things like this. So how do the kernels and the co-kernels relate? So the snake lemma says that I have a map from kernel to kernel to kernel. The snake is right here. Oh, I draw the snake in color. It's going to be a happy pink snake. There's the snake. So the snake comes around and goes to kernel, co-kernel, co-kernel, co-kernel. So then this is saying that I'm just going to call these K1, K2, and K3. Then K1 to K2 to K3 to C1 to C2 to C3 is exact. So this is called the snake lemma. And David mentioned diagram chases. And a lot of what happens in cohomological algebra is what's called diagram chasing. And what my mission here is, I said I was going to be a homological algebra evangelist, or Czech homology evangelist or something, is to bring you guys to the church of homological algebra and diagram chasing. So I want to claim that diagram chasing is fun and easy. So let's do it. So most of these maps are actually pretty easy to do, and I'm not even going to prove everything's exact. What I want to do is construct for you the connecting map. So the snake, let's call it delta right here. So our snake is delta. The delta even looks like a snake. How about that? It shows that fortune is smiling upon us. All right, so how do we construct the map? So I got to go from K3 to C1. All I'm going to do is build the map, and then you guys should actually, if you have not done this exercise before, you should prove that it's a well-defined map. So I got somebody here in K1. So what does that mean? That's the kernel of this map. So I'm going to take alpha element of K3, and that means in particular that D3 of alpha is 0, right? It's by definition. Now, this is a commutative diagram, right? So that means, let's call this little, I don't know, let's call this little a1, little a2, little b1, and little b2 for the maps here. So in particular, D3 of alpha is 0. So, and this map is surjective. A2 is surjective. So there exists what should we call it? You guys give it a name.
Alpha.
No, I can't call it alpha. What do you want? Alpha what? Alpha 2 and A2. Alpha 2 and A2 such that such that A2 of alpha 2 is equal to my alpha, right? So I got some element here. This is surjective, so I take somebody that nails it, right? You guys all with me? So in particular, what that means now is that D3 of alpha is 0, but alpha is A2 of alpha 2, and this means that D3 A2 alpha 2 equals 0, right? So I run the diagram this way, zoop, zoop, I got 0. But that's the same thing as running the diagram this way, zoop, zoop, right? So that means that this is the same thing as B2 D2 B2 D2 of alpha 2 equals 0, right? You guys are all with me here, right? So run the map this way, I got 0. Run the map this way, I got 0. 3 to 2. Okay, so in particular, that means that B2 of D2 equals 0. So D2, right, is D2 of alpha 2 is in the kernel of this map, but this is exact. So being in the kernel of B2 means I'm in the image of B1. So that means that this says that that my D2 of alpha 2, this is equal to B1 of some, let's just call it beta. You guys with me here? We're just chasing the diagram. So the D2 of alpha 2 is B1 of beta. So I got what have I produced? I found some gadget, gal or girl, B over here, right? So I've produced a beta in B1, right? And now I just push it forward, and that's my image. So I push beta forward, so beta is equal to the image of my connecting map. So my beta is the image of delta. And that's it. Now, what do you have to do? So we found this map. There were lots of choices we made, so you have to check that modulo images, the choices were OK. But that's it. It's not so bad, right? So you chase the diagram, and you find your result. So this is called the snake lemma. And from the snake lemma, it is an easy inductive exercise, again, which you should do if you haven't done it, to prove, I'll call it the fundamental theorem of homological algebra, which is that a short exact sequence of complexes gives a long exact sequence in homology. What does that mean? Short exact sequence of complexes means that I have, so short exact is something with zeros on the ends and 3 middle terms. So I have something like A0, A1, A2, 0. No, I don't want to do that. Let's do A0 to B0 to C0. And then I have an A1, a B1, C1, and on and on. And this will be, we'll write this as A bullet, B bullet, and C bullet. You guys are all with me on this, right? So to say it's a short exact sequence of complexes, these are complexes, so there's homology in the rows, but the columns are exact, right? So that's what it means to be a short exact sequence. And then this long exact sequence in homology says that I go from HI of A, so I have homology here to HI of B, goes to HI of C, goes to, it loops around just like the snake, goes to HI minus 1 of A, and keeps going, right? Everybody's with me on this. So this is a long exact sequence in homology. And all this is, this is trivial if you have the snake lemma. This is just an easy application, which, again, you should do app of the snake. All right, so a couple last facts from our homological algebra basics. Let's see, what else did I want to say here? I want to say something about chain homotopies, and I did cheat a little bit. So the first thing that I cheated on here was another little exercise. So let's do one last diagram chase exercise, which is that if I have a map of complexes, so if I have a map from AI to BI, say AI plus 1, BI plus 1, AI minus 1, BI minus 1. So a map of complexes is just something where, let's call this alpha I plus 1, alpha I minus 1. Let's call the differentials DI plus 1, DI, delta I plus 1, delta I. So a map of complexes is simply a map between these things such that the whole diagram commutes. And then it's an easy exercise that a map of complexes induces a map on homology. So again, last diagram chase, how would we see that? So let's see the map on homology. So let's suppose that alpha is an element of HI of A, right? So this is my complex A, this is my complex B, right? So in particular, that means D alpha goes to 0. But in particular, right, so D alpha goes to D of alpha I is 0. So then if I continue to push forward, since D of alpha I is 0, that means, of course, that bad, terrible notation. X. Dx is 0, right? So dx goes to 0. If I then push forward by alpha, that means, of course, alpha dx equals 0. So I had 0 this way, then I continue pushing around, I get 0. But alpha of dx is the same thing as delta of alpha of x. And so in particular, alpha of x is in the kernel of delta, right? So that means, and then you got to check that up to the images you're good. So this means, but it certainly means that alpha of x is in the kernel of delta. And so you get a map on homology after you check it. So that's another example of diagram chasing. Last thing I want to say about diagram chases is about chain homotopies. So if I have a sequence, did my audio go out or not? Still okay? Yes? Yes, okay. So suppose I have maps of complexes. So I have two maps. Let's call one of them alpha. I'm just going to write it as alpha and beta. It's indexed by where it is. So you say that two maps are homotopic. So alpha is homotopic. Chain maps are homotopic if alpha minus beta equals, if there exists a map gamma. So the gamma map goes backwards. So I have maps gamma. And the gammas, again, are for each index. And so what do I get? If alpha minus beta is equal to delta gamma, I'm not putting the indexes in, delta gamma plus or minus, let's see, plus. So I go gamma and delta, but I could also go d and gamma plus gamma d. So this is the definition of chain homotopy. And so then chain homotopic maps, this is chain homotopy, H-O-M. Well, David's allowed to misspell things, so I'll just call it chain hoto. Induce INDUCE iso on homology. All right. So that was our homological algebra basics. I'm going to write that as an exercise for you guys. So you should do that. And the last thing I wanted to remind you of was relative homology. So if I have, last definition, relative homology. So if y is contained in x, I have the I chains on y sitting inside the I chains on x. And then I can quotient by this, so I have CIX mod CI of y. This is a short exact sequence. And by the fundamental theorem of homological algebra, short exact sequence of complexes gives us a long exact sequence in homology. So this yields a sequence, something that looks like hi of y goes to hi of x goes to hi of x comma y. This is called the relative homology, is the homology of this quotient complex. So that's relative homology. All right, so now we're ready for derived functors. So 20 minutes left to do all of derived functors and check homology. So I'm actually going to go over time by probably 10 minutes here. I want to do them at least some amount of justice. So, but we can do a pretty good job. So derived functors. So really what derived functors are an exercise. What we did with the diagram chasing over there, all it is you just fancy it up a little bit. So it's not that bad. So the first thing I need to remind you of is definitions of projective objects and injective objects. For us, remember, we're in the category of modules. And so a projective module, P is a projective module, if anytime I have something that looks like A goes to B goes to 0, this means this is a surjection, and I have a map from P to B, then I can factor the map. So there exists a map backwards so that the whole diagram commutes. That's the definition of projective. The easiest examples of projective objects are free modules. If this is a free module here and I have a map here, I can just follow my nose and do what I want here, right? So free modules or projectives, those are easy. Dually, there's a notion of injectives. And it's exactly when you do that, you just reverse all the arrows. I is injective if I can split the map like this. So what's interesting is you think, okay, free modules are an easy example of projective modules. Injective modules are really quite nasty. So when you start reading Hartshorne and learn about injectives, they're good theoretically, and this is sort of a manifests itself in derived functors, is that injective modules are very good theoretically, but you're never going to compute with them. Okay, so anyhow, that's injective. And now let's remember what a functor is. If I have two categories, A and B, these are categories, so A has objects and morphisms. B has objects and morphisms. Then a functor from A to B is going to take the objects of A to the objects of B, the morphisms of A to the morphisms of B, and a functor has to do two things. It has to preserve the identity and compositions. So it does the things you would want, otherwise it would be too general. And so I want to now remind you of sort of suppose that there's two flavors of functors, and it's called covariant and contravariant. So if I have a map from A1 to A2, these are objects over here in A by F, then I can apply my functor F. It spits out a sequence of things in B, so I have F of A1, F of A2. These are objects in B. I have F of F. This is called a covariant functor. All the directions are preserved. So this is covariant. And if the arrow gets reversed, this is contravariant. So let's see some examples of covariant and contravariant functors. So covariant. So what's one that we've seen in this course? It's a covariant functor. That's not the one I want. I wanted global sections. How about tensor product? Tensor product preserves the direction, right? Yes, when I tensor with an object, tensor product is covariant. What about HOMs? Say I'm homing into, I'm just going to leave it there, L or HOM. All right. So if I take a short exact sequence, or I don't even need an exact sequence, if I have B to C, and I have a map L like this. So I fixed L. I have a map from B to C over in my source category. I have a map from C to L. How do I get a map from B to L? I follow the arrow, right? So in particular, this is going to be what? Contravariant. On the other hand, if I do it this way, L maps to B, then follow that diagram. So this one is covariant, right? All right, so there's a good stable of some examples, and we're not quite done yet. So the other thing that functors have the property of, so let me define it. So we say that a functor is F is left exact if it preserves left exact sequences. And similarly, I won't write it out. Right exact if it preserves right exact sequences. So global sections, we saw that it was what kind of, is it got any kind of exactness property? Left exact. So this guy's left exact, or gal is left exact. How about tensor product? Right exact. How about HOMs? They're both of these things are left exact. So what derived functors are, let's do something. So suppose that let's do the silliest one. So suppose I have a short exact sequence of sheaves. Then when we hit this with global sections, we know it's left exact and covariant, so we have this. And we have a mystery person that shows up, right? And so a left exact covariant functor has what are called the right derived functors. And the point is, what you're plugging in is over here on the right, right? So it's weird because you had a left exact functor, but you get right derived functors. And that's where the terminology comes from, is you're filling in the diagram over on the right. So the right derived functor, this is what the right derived functor. And it is of our functor h0. So this is typically called R1 of h0, and it's going to be written in our case as an h1 of the Sheaf homology. All right, so that's the definition. How do you compute these things? So that's what they're designed to do. These derived functors are supposed to fix the lacuna that appears when a functor is not exact. So in particular, exact functors are going to have no interesting derived functors, right? Because so for example, localization is an exact functor, so you don't get any derived functors. So how do you compute these things? So now the question, so for me at least, I'm a computational person, so how do you compute these? So the recipe to compute, and I'm only going to do it because the one that's germane to us is Sheaf homology, which is left exact and covariant. But there's a little 2x2 table that says left, right exact, covariant, contravariant that says what kinds of resolutions you need to take. So here's the recipe to compute. So if I have f, a left exact, covariant functor, then I'm going to tell you what Ri of f of a is. So a is some object, right? So a is an object. This is on, let's say, and a is an object. To compute this is by definition, this is hi of 0 goes to I0, goes to I1, goes to I2, goes on forever, where this is an injective resolution of the object A. In other words, it's not there, but if I penciled in like this would be an exact sequence, okay? So I take an injective resolution, I drop the object itself, and I've got this. And then I just compute the homology of this, and that's it. Those are how I define the derived functors. So your objection, which you should make, is, number one, is this even well defined? What if I take a different injective resolution? It's an exercise that it doesn't depend on the choice of injective resolution. So the more unpleasant point is what I said is you're never going to be able to find injective resolutions. So, but it doesn't matter because these things are good theoretically. So that's the definition. So exercise, show that the Ri f of A don't depend on choice of resolution. And it's not so bad because you can guess that you take a different injective resolution, I prime, right? And then I'm going to have, because of the properties of injectives, I'll get maps between the resolutions, right? And then you play the game that you would expect with our homological tools. So the reason that they're useful is a short exact sequence of objects yields a long exact sequence in derived derived functors. All right, so this is what we would like. And again, this is an exercise that's not so bad to do. So you take a short exact sequence of objects, you take the injective resolutions of all of them, you patch the injective resolutions together, and then you show that you get a long exact sequence in the derived functors. In particular, what that means is for Sheaf homology, if I had a short exact sequence of sheaves here, what's going to appear over here, we can now erase our ambiguity. This would be h1 of f1 goes to h1. Yeah, I'll get you in a sec. f2 goes to h1 of f3 goes to h2, f1 on forever. Yes, I heard a question. I thought I heard a question. No question? All right. So there was, I won't pick on anyone, but there was someone who said that they were not enamored of homological algebra. And I get it, because if I told you, okay, so here's some theory, but I can't actually compute them, for me this is useless, right? I can't do examples, so I want to do examples. So what we're going to do now is switch gears to the last topic, which is now gone, which is check cohomology. I think that's all. Let me just make sure that that's all I wanted to say about derived functors. Yeah. Okay, so check cohomology. So now section 4, check cohomology. So that was pretty fast. That was derived functor cohomology in 10 minutes. So, but it's not so bad, and it's really all just chasing diagrams. So check cohomology. So this is the way that sheaf homology was first defined. And the idea is the following. Let's be super pedestrian. Suppose we have two open sets, U1 and U2, right? And I have some sheaf. So a sheaf is going to tell me I've got some object f of an U1. I've got some object f of U2. Of course, U1 intersect U2 is another open set. These are just algebraic things. Maybe they're sheaves of Z modules, which is just some abelian groups or whatever, right? Everybody's with me on this, yes? And now the thing is, a typical problem that you have in algebra is you had some local data, right? So I have local data on U1, local data on U2, and I want to find a global object, right? So I want to find a global object. The sheaf axiom says exactly that if I have some f that lives on U1 and it restricts to something on the intersection, I have somebody over here that restricts to the intersection and they agree on the intersection, then I can glue, right? That's the sheaf axiom, says I can glue. And so the idea is that if I wanted to sort of write an algebraic measure of how things glue, is I would take them and I would map here. I would take F1, F2, and I would just send them to the difference on the restriction. And then the sheaf axiom says that the kernel of this map is exactly the global sections, right? That's exactly what we, in the case of this two cover. So this kernel equals gamma of whatever our sheaf is, f, equals global objects. And so that's exactly what check cohomology is designed to capture. So now I'm going to define check cohomology for us. So suppose that I have some open cover U in open cover. And F some sheaf. I'm going to define the check cochains. So CP check. I'm going to define a differential on the check cochains. CP plus 1 check. So what I want to do is I want to think, let's write this like this. I want to think of a P cochain as something, think of as assigning to an index to a P plus 1 tuple an object. So what I mean by that will become clear in a second. So what I'm going to do here, this CP is the product over all, let's say, gamma is in, I think we call it L sub p in our book, but these are all P plus 1 tuples of f of, I'm going to write U sub gamma equals U I 0 intersect U I p. Right, so I take so I have a P plus 1 tuple. I had an open set. I take the intersection of that. That gives me some open set. F of that is an algebraic object, and I take this P. These P chains are over all such things. Right? You guys are with me on this, right? And now, so suppose what's this dP thing? So then I've got, let's say, alpha's in here, and then I send my dP of alpha over here. What is this? So what I have to do is tell you the recipe that I'm thinking of, the cochains is doing is something it assigns to a p plus 1 tuple. So now this thing's going to eat a p plus 2 tuple, right? So I want to feed this thing a p plus 2 tuple. So what do I do? So I feed this, so this thing wants to eat a p plus 2 tuple, and what it's going to do is it's going to be an alternating sum, j equals 0 to p plus 1, minus 1 to the j. And I take, so gamma here, I've got some gamma that's a p plus 1 tuple. Gamma equals, let's say, k0 up through kp plus 1, a p plus 2 tuple rather. And what I do is I take alpha of k0 up through k sub j, leave it out, k sub p plus 1. All right, so what have I done here? Alpha was living over here. It knows how to, you hand me a p plus 1 tuple, it knows what to do, right? Alpha knows what to do with a p plus 1 tuple. It doesn't know what to do with a p plus 2 tuple, which is what I handed it. So what I do is we handed a p plus 2 tuple. We just take an alternating sum of leaving out the j thing. This is a p plus 1 tuple, right? Alpha knows how to operate on that. And then we restrict it to our u sub gamma. Now, that seems a little disconcerting at first, but what you should keep in mind is really this recipe is exactly what we had for simplicial homology, and that's really what's going on here. So if you write down, and we'll do this tomorrow in the lecture on sheaf homology, when you write down what the differential looks like on the open sets in terms of just plus and minus ones, this really is just the same thing as a simplicial differential. You think of one of these things as a p simplex, and then this thing is really just the differential on a p simplex. So that's what this is. So this is the definition of the check cohomology. And so then, easy exercise, d squared, I guess I should be fancy and write my d's with little checks on top, is equal to 0. So this really gives me a complex. So then we define the check cohomology of a sheaf and a cover as the cohomology of such a thing. So, definition, HI check of a cover in a sheaf is equal to HI of check U, where this is this check of U. All right. So, bad news. That's a definition. This depends on the choice of cover. Here's an example that you should do tonight after the soccer game or during the soccer game. Take S2. Take the cover where I use sort of I glue some sort of the top of a tetrahedron, so something like this. This is supposed to be 3 triangles, but hollow here, and then same thing, 3 triangles. This is hollow right here. This is hollow right here, and I glue them together, right? So I have my open sets are 2 things, so I have 2 open sets. So you can see, right? And let's say with z and I'm going to use the constant sheaf. Z is the constant sheaf. In other words, to each open set, I'm just assigning a copy of Z for the Canadians there, right? So my check complex is going to basically be Z2 goes to Z, right? Because I have my 2 open sets. There's only 1 intersection here, so I'm going to have that. You guys are with me here, yes? I have 2 open sets. That's my C0. I have 1 intersection. That's my C1. I got nothing else. When I compute the cohomology of this, I only have position 0 and 1. I'm never going to have an H2 of this, right? So it's too small a cover. Whereas, so the other exercise is if you take, let's say, we take our tetrahedra, which is hollow tetrahedra, which is topologically an S1, and we cover it with the 4 triangles, fatten them up a little bit, right? So fatten the 4 triangles. The 4 triangles. And this is a good exercise to do. You should try this if you haven't done it before. Then I have 4 open sets, so I'm going to have something like a Z4. And then I've got my intersection. I'm going to have 6. 4 choose 2, so I'm going to have Z6. And then you can check that I'm going to go to a Z4. And so, and when I look at all the intersection of all four, I get nothing. So I have something like this. And when you actually write down the differentials using our recipe over there, you'll see that you actually get that H2 of this cover, let's call this cover U, and Z is isomorphic to Z, which is what we would have liked to see for S2, right? So this is cover dependent, so this is bad news. This is frowny face. But we have a fix. So the fix is somewhere in chapter, David, do you remember where we define direct limits? Chapter 6, okay. Chapter 6, direct limits. So I'm going to now order all open covers. So here's two open covers, V and U. I'll say that V is subordinate to U if for all open sets V and V in V exists some open U in U with U contained in V. So this is called a refinement. Right? So this is bigger in this order if it's got a finer collection of open sets, right? And so then there's this notion of a direct limit that I'm not going to do at this point in the day, but then we can say that the ith check cohomology of xf, notice I'm not cover dependent, this is going to be by definition the direct limit over this ordering on my open covers of hi check of uf. So this is again a terrible definition, right? I can never take all the open covers, right? So this is, okay, so that was bad news. This is even worse. That's not much of a fix, right? It's not much of a fix. But there's a light at the end of the tunnel. So here's the light. We turn our frown upside down because we're almost done. So the happy news is if we have a nice open cover, and I'll say what nice is in a second, we can actually, nice open cover U, smiley face, right? That's a nice open cover. We get that hi check of uf is actually hi check of our use of smiley face f, right? So the question is, how do we find one of these nice open covers, right? So I don't want to take some direct limit.
Just hi of xf?
Yeah, that's what I meant. Yeah, that's right. Thank you. hi check of xf. So the check cohomology can be computed for a decent cover. And the answer, this is usually called the Leray cover. So, and what is a good cover? So theorem, is it Leray or Serre? I think this is it Serre or Leray? I think I want to say Leray, and we can go back. If U a cover such that hi check of U so if there's no higher cohomology on any of my open sets of the cover, then this is called a Leray cover, and this computes such a cover, then U computes the check cohomology. So that's Leray cover. Here's the theorem of Serre. If U is an open affine and F is quasi-coherent, then this condition holds. So what's the point? By appealing to Serre and Leray, this tells us that if we have an affine open cover for a quasi-coherent sheaf, this is always the situation that we're going to be in the toric case. That's good enough to compute check cohomology. But this still hasn't answered a question, right? So these are, is everybody with me on this, right? So this is saying that open affine is a something you can compute check cohomology with, but we still haven't answered the question, or we should have asked. What's the question I should ask? Is it time to finish? No, that's not the question. Are we done yet? It's not, are we done yet? What's for dessert? That's not the question. Is there beer? Is not the question. That's David's question. Help me out. Is it compared to the other? So the question is, how does this compare? I mean, I went through this whole rigmarole of how does this compare to this other definition, to the derived functor. See, fun is in there for functor def. And the answer is actually pretty easy. It's a good place to end. So maybe I just do it right here. So the idea is what? Suppose that what I can do is I can take, for a check complex, these are modules, right? But I can sheafify modules. And so step one is to sheafify the check complex. So I have some picture like this. So 0 goes to F, goes to C. I'm going to write this curly. This is sheafified version of the check complex. So this is sheafified the check complex. Now I don't want to write it there. This is what that is. That's the sheafified check complex. But I also can take the derived functor thing. So I can take an injective resolution. Right? So I have these two things. So I won't prove the whole thing because it's late and we're all tired. The point is that, of course, I have an isomorphism there, right? And so what do I have? That means I have an inclusion. 0 goes to F, goes to I0. On the other hand, I have a map from F. Oh, I want my I0 up here. I have a map from F to C0, right? So I have this inclusion up here. I certainly have a map from F to I0 here. And so what do I get by the injectivity? Injectivity gives me a map right here, right? So I get a map from here to here, and then as soon as you're done at the first step, you percolate it out. So what I get is a map from here to here, and that means by our fundamental, well, one of our fundamental theorems, I have a map of complexes, so I get maps from HI of this C to HI of derived DF, stands for derived functor of F. And you can check that that's actually an isomorphism. I'm not going to do that. And the way you check it's an isomorphism is you do that. The reason I had that chain homotopy definition is you show that these are chain homotopic. And that's it. So we covered a huge amount of material, but we've, I think, hit on all the key points that we need for tomorrow for cohomology, when we're going to do this in a very, very concrete setting, in the case of torics and our God-given open cover. And if you're an atheist, it's the cover given to us by, I don't know, by
kids, if you agree to be videotaped, please pick up this.
I did have a couple of things I was going to say more about Serre duality, but we'll just do them tomorrow.